Hi, everybody. It's Professor Mitchell. We've reached the last section of Chapter 7, which is Section 7.7 on simplifying complex fractions. In this section, we're going to simplify complex fractions by simplifying the numerator and denominator and then dividing, which we will call Method 1. Then we'll simplify complex fractions by multiplying by a common denominator. We'll call that Method 2. And then we'll end by looking at simplifying expressions with negative exponents. And we're back on SLOB, which is where we spent most of this chapter. All right, so what is a complex fraction? A complex fraction is a fraction that has fractions in its numerator and or denominator. What you're looking at here is one of the first memes that I ever created when I was giving this definition to a class one time. This just kind of created itself in my head. And then the example you're looking at here is really the simplest type of complex fraction that you could hope for. Notice that there's just one fraction in the numerator and one fraction in the denominator. So let's look at how we would simplify that. All right, so there's our example. Believe it or not, we've done problems like this before. They just weren't exactly written like this. Remember that a fraction bar means divide. So let's think of that big fraction bar in the middle as division, and we can write this problem as 7y over x squared plus xy divided by y squared over x squared. And we did problems just like this back in section 7.2. So you remember what to do, right? We're going to change that to multiply by the reciprocal. So it'll be 7y over x squared plus xy times x squared over y squared. And then remember, in order to multiply those, we're going to simplify as we go along, which means that everything has to be factored. Everything here is factored except what you see on the bottom left. I'm just going to scoot over here so that I have room for my answer. So when I go to factor x squared plus xy, that's just a GCF. I'm going to pull out x. Leaves me x plus y, multiplied by x squared over y squared. So now I think I see two pairs of common factors. I can get rid of this x and one of these x's, right? X squared divided by x is x. And then I can do y squared divided by y is y. So the y will be on the bottom because that's where the y squared was. And that is going to leave us with 7x over y times x plus y. And you can leave your answer just like that. All right, so let's go back to the presentation, start talking about methods 1 and 2. All right, so method 1 is to rewrite the numerator and denominator as single fractions, then divide. And here is our example. All right, so, well, let's switch over to the tablet and then we can talk about what we're going to do. Okay. So the reason this is a good example for method 1 is that the numerator is already a single fraction. So all we have to do is make the denominator a single fraction. So we're going to take this thing right here and combine it into one fraction, just like we did in section 7.4. All right, so that means we need a common denominator for that, which would be x times y, right? Okay, so in order to get that common denominator, I need to multiply the top and the bottom of this one by x, and I need to multiply the top and the bottom of this one by y. So that is going to give me x squared minus 9y squared over xy over xy minus 3y over xy. So now that those two little fractions in the denominator have the same denominator, I can subtract them. Not doing anything with the numerator right now. Okay, so we'll just write that denominator as x minus 3y over xy. And now this looks an awful lot like the problem that we did in the last example. So this would be a good time for you to pause the video and try to finish this one. And I'll be here waiting when you get back. La, 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 la. Okay, you tried that? So let's write that as x squared minus 9y squared over xy divided by x minus 3y over xy. What do you think? You think I can squeeze this answer in on this screen? Let's see. Write that as multiplication. No, I don't think I can. Okay, so we're going to flip that second one and change it to multiplication. xy over x minus 3y. All right, so now we can get rid of the x's and we can get rid of the y's. I could have just gotten rid of them both at the same time. All right, and now going over to the next screen, I'm left with x squared minus 9y squared over x minus 3y. So the only question now is, can we simplify that? Well, I guess we won't know until we factor. Notice that the numerator is a difference of two squares. That factors into x minus 3y times x plus 3y. Oh yeah, we can simplify this. All right, so now we say goodbye x minus 3y. And believe it or not, that big messy thing that we started with simplifies all the way down to x plus 3y. All right. So let's see what else we got. You're going to have another chance to practice that a little bit later. Okay. All right, but first I want to show you method 2. So I personally like method 2 better. It feels like a little bit less work to me. So if I was stuck on a desert island and I could only bring method 1 or method 2, I would probably bring method 2. Conceptually, sometimes people find this one a little more difficult to understand, but do try because I really like this method. So we are going to multiply the top and the bottom of the big fraction by the LCD of the little fractions. And here's the example. So let me show you what I'm talking about. All right, here it is. So we're going to simplify this expression using method 2. All right, so the idea behind method 2 is you find one LCD that covers all of the little fractions in the whole expression. So notice there are 4 of them. The denominators are x minus 4, 4 minus x minus 4, and x. All right, so what would we have to include in the LCD there? Well, it would definitely have to include an x, and it would have to include an x minus 4. It does not, however, have to include a 4 minus x because remember, that's just the opposite of x minus 4. So we can actually get by with just x times x minus 4. All right, so here is the idea behind method 2. You're going to love this. I'm going to take my expression, 3 over x minus 4 minus 2 over 4 minus x all over 2 over x minus 4 minus 2 over x. And I'm going to multiply that big fraction by x times x minus 4 on the top and the bottom. So notice what I'm really doing is just multiplying this big fraction by 1. Okay. So now the way that we're going to get rid of all those little fractions is we're going to distribute our LCD. All right, so what's going to happen is you get an x minus 4, and you get an x minus 4, and you get an x minus 4, and you get an x minus 4. And the first time I ever said that to a class, this created itself in my head. All right. Okay, so here we go. Just waiting for my tablet to catch up here. There it is. All right. Okay, so when we distribute those x minus 4s, here's what we end up with. Let's see, I will go ahead and just write x minus 4, leave a space there, x minus 4, x minus 4, and you get an x minus 4. Okay, and those are all parked next to my different little fractions. Okay, all over. These problems do tend to take up a fair amount of space. Okay, so what I would recommend you do now is put those x minus 4s over 1 if that's something that you tend to like to do. All right, and now my favorite part, we get to cross stuff out. All right, so in the first little fraction, the x minus 4 cancels. Let's save the top right for last. In the bottom left, x minus 4 also cancels. In the bottom right, the x cancels. Okay, now top right, do you remember how that works? We have a 4 minus x and an x minus 4. I can cross those out as long as I promise to do what? Leave a negative 1. Remember that trick? All right, so once we clean this up, it's going to look a lot nicer. Oh, let's see. I'm trying to take a snapshot of this to put in the short-term memory. It's going to be 3x plus 2x over... Okay, well, I'll come back and double check this, but I think it's going to be 3x plus 2x over 2x, and then it's going to be minus 2 times x minus 4, right? Here is the 3x. Here is the plus 2x. That negative 1 turns this into plus. Here is the 2x. And here is the minus 2 times x minus 4. This is where I miss having a real whiteboard. All right, 3x plus 2x is 5x. And then downstairs, I will distribute this negative 2. And that's going to leave me 2x minus 2x plus 8. So believe it or not, that big nasty expression simplifies all the way down to 5x over 8. Ta-da! All right, so now I want to give you a chance to practice this. So let me go back to presentation. I've got 2 examples. So I am not going to tell you which method to use. I'm just saying pick the method that seems easier, all right? So, and I've said this to you before about something else, you know, give both methods a fair shake. But if it turns out that you like one much, much better than the other one, then feel free to use that one all the time. It's fine. We do some complex fractions in pre-algebra. In pre-algebra, I don't think we get the alphabet involved. But something I discovered one of the first times I taught complex fractions in pre-algebra was that pre-algebra students absolutely hate method 2. And they want to use method 1 all the time. My experience with Math C students is it's about 50-50. All right. Some people like method 1 better. Some people like method 2 better. All right. So please pause the video and try both of these. And then when you come back, I will tell you which method I like better for each one. But as long as you got the same answer, that's what's important. Okay. So I'll see you when you are ready. All right. So I hope you're ready to compare notes. For this one, I chose method 2. Because I noticed that there's more than one fraction in the numerator and the denominator. So I don't really feel like combining both of those. I just feel like method 1 might be a little bit more work. So I'm going to use method 2, but if you use method 1, that's fine. The only thing that's important is, do we get the same answer? All right, so the LCD that would cover all of the little fractions in this whole expression is x squared, right? So we're going to multiply the top and the bottom of the big fraction by x squared. So you get an x squared, and you get an x squared, you get an x squared, you get an x squared. All right, so let's see, how is that going to look? Oops. Okay. So we're going to have an x squared, let's say here, 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 and here. So 2 over x squared plus 1 over x all over 4 over x squared minus 1 over x. All right, and once again, I will sneak a 1 underneath all of those. All right, now my favorite part, I get to cross stuff out. So in the top left, the x squareds cancel, and also in the bottom left. In the top right, I can cancel an x, take out this x, and that would leave an x. And the same thing on the bottom right, take out this x, and that would leave an x. So that is going to leave me with 2 plus x over 4 minus x, right? Can you simplify that? No, you can't. I would leave it just like that. All right. So method 2, yeah, we got that done in about 2 steps. All right, so now let's look at our other problem. As I said, I would be happy using method 2 all the time. But for this one, I'll use method 1. Method 1 shouldn't be too bad because the denominator is already one fraction. So I just need an LCD for the top. Okay. And the LCD for the top of the big fraction happens to be x plus 2, x plus 7. All right, now remember what we're trying to do with that numerator. We're trying to combine it into one fraction. All right, so don't just multiply through by x plus 2, x plus 7, because that's going to change the value of the big fraction. All right. If you wanted to do that, you would also have to do it to the bottom of the big fraction, and then you'd be using method 2, which is fine. But if you're using method 1, then all you want to do is just multiply the top and the bottom of this one by x plus 7. And then multiply the top and the bottom of this one by x plus 2. All right. So that is going to give us a great big fraction where in the numerator we have two little fractions with denominator x plus 2, x plus 7. The numerator of the first little fraction is now 2 times x plus 7. And the numerator of the other little fraction is now 6 times x plus 2. All right, and we haven't done anything with the denominator. It's still 4x plus 13 over x squared plus 9x plus 14. All right, so since the two little fractions in the numerator have the same denominator, we can combine those. And hopefully you won't mind if, I hear a lot of students ask me, Mitchell, do I have to show all the steps that you're showing? Well, no. I mean, you should show almost as many as I'm showing, because when you skip steps, that's when you make mistakes, right? All right, so just this once, I'm going to do two things in one step. First, let me copy this, and then obviously I'll go over to a blank screen. Okay, so what we're doing, let me put a little dotted line here, just kind of cramming it into a small space. And all right, we're combining those two little fractions into one fraction with denominator x plus 2, x plus 7. All right, and then let's do this. Bring in our two numerators where I have first distributed the 2. So that's going to give me a 2x plus 14. And then in the other fraction, I've distributed the 6. And so that's going to give me a 6x plus 12. Okay. So hopefully you're following that okay. I don't think I've maybe ever said this to you in a video. One thing that I think would be a very good idea when you're watching these videos and taking notes, if there's ever a time that I say something too fast or skip a step that you really needed to see, write yourself a note, like in the margin of your notebook, and then ask about it either during that week's discussion, or you can even send me an email. Mitchell, you said something at the 9 minutes, 7 seconds part that didn't make sense to me. And then what I'll do is I'll pull up the video and see what I said at the 9 minutes, 7 seconds, and I will explain it to you. All right, so let's go over to the next screen. And I'm just going to copy what I had there. So it said 2x plus 14 plus 6x plus 12 all over x plus 2, x plus 7. And that is divided by 4x plus 13 over x squared plus 9x plus 14. All right, so this looks an awful lot like the very first example we did. There's one fraction on top, one fraction on the bottom. So let's change that into a division problem. Notice I also have some like terms up here, which I will go ahead and combine. So instead of writing 2x plus 14 plus 6x plus 12, I'm going to write 8x plus 26 over x plus 2, x plus 7. And that is divided by 4x plus 13 over x squared plus 9x plus 14. Almost done. All right, change that into a multiplication problem. All right, now hopefully what I'm about to say to you is okay. A couple minutes ago, I said just this once, I'm going to do two things in one step. I've already done it once since then, and I'm about to do it again. So even as I was saying it, I knew that just this once was probably a lie, but all right. So I'm going to flip this over. which is going to give me 4x plus 13 downstairs. And while I'm at it, would it be okay if I factored that x squared plus 9x plus 14? Because to do this multiplication problem, obviously we have to factor. Well, guess what? When you factor x squared plus 9x plus 14, it factors as x plus 2, x plus 7. I think they rigged this problem that way. All right, so we can say goodbye to x plus 2. We can say goodbye to x plus 7. That is going to leave us with, I think I can finish this problem up here in this space. All right. I didn't leave a blank screen on the next slide, so I would like to try to finish it here if I can. That leaves us with 8x plus 26 over 4x plus 13. Well, guess what? We're not done simplifying because you can factor 8x plus 26 by just pulling out a 2. And look what you're left with when you pull out that 2. You're left with 4x plus 13. Oh my goodness. You get rid of that 4x plus 13, and this big nasty expression simplifies down to 2. Unbelievable. All right. It happens. It happens. All right, so I just have one more thing to show you. Is negative exponents, expressions with negative exponents. So one of the things that we cover in beginning algebra, I keep saying we used to cover in beginning algebra. We still do have a couple of courses where beginning algebra is taught. One of them is Math 61, which I'm thinking that I might teach sometime in the future. All right. So if you're a Math C student, then you would not have seen this, except maybe in high school. But if you're a Math 61 student, then you would have seen this, I don't know, a few weeks ago when we did chapter 5. The negative exponent rule, a to the power negative n, that means the reciprocal of a to the n. So if you're a Math C student, this is something I definitely covered in your review quiz at the beginning of the semester. All right, so even though this example that I have written down here does not look like a complex fraction problem, it is a complex fraction problem when you rewrite it without the negative exponents. All right, so one last time, let's switch over to the tablet. Okay, here we go. A to the negative 1 plus 2a to the negative 2 all over 2a to the negative 1 plus the negative 1 power of 2a. All right, think about the difference between those two terms in the denominator. All right, so according to the negative exponent rule, a to the negative 1 would just be 1 over a to the first, or just 1 over a. Okay. Now, where people tend to get confused is when I get to something like 2a to the negative 2. Let's talk about that down here. Notice this negative 2 power does not apply to the 2. It only applies to the a. So you want to make sure you think of this as 2 times a to the negative 2. And then remember that a to the negative 2 means 1 over a squared. Just wait, there we go. All right, so for that reason, 2a to the negative 2 means 2 over a squared. Okay, so that's going to go here. And 2a to the negative 1 is very similar. That would mean 2 over a to the first, or just 2 over a. Okay, so now let's get rid of this. And let's talk about the negative 1 power of 2a. Because the 2a is in parentheses, that means that the negative 1 power does apply to that whole thing. So this is just another way of saying the reciprocal of 2a. So the whole entire 2a is going to go downstairs. And that's what this is doing in the section on complex fractions. So now you just have to decide, do you want to use method 1 or method 2? This would be a good time to pause the video and try to finish this problem off. I'm going to use method 2. Surprise, surprise. So the LCD that would cover all 4 of these little fractions would be 2a squared. So let's distribute that 2a squared. All right. So we have 1 over a, we have 2 over a squared, we have 2 over a, 1 over 2a, and then we are going to park our 2a squared next to every single one of these. All right, and then put the 1 underneath if you find that helpful. All right, and now my favorite part, get to cross stuff out. Can take an a out of here, and that leaves an a upstairs. Here we can take out the whole entire a squared. Down here we can take out an a. And then here we can take out a 2 and also an a. All right, so after you pick through the trash and grab what's left, you have a plus 4 over 4a plus a, right? Oops, 2a plus 4 over 4a plus a. All right, I almost missed this too. All right, 2a plus 4 over 4a plus a. The only thing I would say you should definitely do is combine the like terms downstairs. That would give you 2a plus 4 over 5a. Can you simplify that? Well, no, I think it's pretty clear that the numerator and the denominator don't have any common factors. The only factors on the bottom are 5 and a. And I think it's pretty clear that 5 and a are not factors of the numerator. So we are done with that problem. We are done with section 7.7. And we are done with chapter 7. All right, so we'll see you next time. We'll start chapter 8, which is a pretty short chapter. We'll see you then.